Hello, meteorology students. Welcome back to Meteorology 10, Weather and Climate. This is the first video of three videos that we'll have for the week. Today, we'll be talking about stability. Well, in this lecture, we'll be talking about stability, what a stable atmosphere looks like, an unstable atmosphere. We'll look at conditionally unstable, and then we'll also look at some lapse rates. We'll look at dry, moist, and also environmental lapse rates. So let's get started. All right, so the first thing that we're going to talk about is stability. Stability might be a little different than what you might think of, though. So, when something is stable, that means it is going to go back to its original place, its original place that it was at to begin with. So, we kind of can describe it as a rock on a hill. So a rock if we start with the rock at the bottom of the valley, and you push it, like this guy is right here. He's thinking about something there, and then he decides to push it up to the top, right? And he lets it go. Gravity's gonna pull it back down again, and it's gonna go back down to its original state. That would be like a stable environment or a stable situation that we might see. Another one though is if we take it to the top and then give it a push. Then it's going to roll down the hill, right? Like on this one, and it's not going to end up where it started. That would be more like an unstable situation. So this is kind of how I don't know what that was. Somebody honking. that would be an example of a stable and an unstable atmosphere. Um, Stability in the atmosphere. Now, there's a couple things that can determine the stability in the atmosphere. First, we have wind shear and temperature. These things can determine actually how stable an atmosphere will be. But stability also changes. It will change from location to location, so like horizontally. It'll also vertically change from layer to layer. And then it'll also can change from time to time because the atmosphere is constantly moving. It's not ever like staying in one place. So for that reason, then time also can. Well, if you wait long enough, I guess it can change. Um, okay, so this brings us to an important concept here, and that would be an air parcel. So an air parcel is going to be a theoretical idea, something that meteorologists use to describe the properties of a piece of air. You can look at it, you can kind of think about it as a bubble. A lot of people describe it like a balloon, but without the actual balloon. So the main thing to note, though, is that this air parcel is not going to exchange any properties with the outside air. So it's not going to exchange temperature. It's not going to exchange moisture. It's not going to exchange pressure. It's just going to be its own kind of theoretically closed system. But since it doesn't exchange heat with the environment, we can also call it adiabatic. Adiabatic would be like a vocabulary word for parcels that don't exchange heat. But that doesn't mean that they don't heat and cool. That just means that they don't exchange it with the outside environment. So now there's a couple ways though that air parcels can heat and cool. First of all, through expansion and compression, and secondly, through latent heat release. Now we already went through latent heat release. This is going to be phase changes, which are going to give off or absorb latent heat. I guess that's something to say there. I don't know if you heard that. Okay, so now an air parcel can have buoyancy to it. And this is going to be determined between what the properties of the air parcel is versus the properties of the environment. So if the air parcel is warmer than an environment, it rises. Hot air rises, right? So that's going to be considered positive buoyancy. But if an air parcel is cooler than the environment, it's going to sink. That is going to be an example of negative buoyancy. Okay, so dry adiabatic lapse rate. As an air parcel rises, it cools. Why is it cool? Think back at probably one of the first few lectures that we had. We said that there's going to be an equation called the ideal gas law, right? And it's temperature, pressure, and density. They're all related through the ideal gas law. And all of these things are going to decrease with increasing height. So as an air particle rises, it cools because there's less pressure, because it's in the troposphere and it's cooler with height in the troposphere, also because it's less dense up there. Okay, when the air particle is not saturated, it cools at the dry adiabatic lapse rate. So we actually have a number, 10 centimeters per 1,000 meters. That is exactly how much that air parcel, if it's not saturated. Now, that does not mean that it's dry, like a dry adiabatic lapse rate. Don't think about it as having no moisture inside that parcel. That's not what we mean. All we mean by saying dry adiabatic is that it's not saturated. So you have this air parcel, it's going to rise due to the fact that it's warmer than the environment. Okay, and we know that that air parcel, as long as it's not saturated, will cool at 10 degrees per 1,000 meters. This is going to be kind of what you could imagine it being like. You say you have this R parcel, an air parcel that's 30 degrees here at the ground, and it's going to rise. As it's rising, it's going to expand and also cool. So see how it cooled at 10 degrees, and there's 1,000 meters. This is Celsius. And it's going to rise another 1,000 meters, and then we also have it cooling another 10 degrees. Notice how it's expanding it because it's lower pressure up there, so it's going to have less of those molecules to hold it together, so it'll expand out. It's going to decrease in temperature by 10 degrees every 1,000 meters. Now you can do the same game if it's actually like going down, moving down. So say it's in an environment where it's actually going to be colder than the outside temperature. So if it's colder than the outside temperature, then it's going to want to actually sink. And if it's sinking, then at the same time, it's going to be compressing and it's going to actually be warming. You can see that 10 degrees, then it's going to go to 20 degrees and up to 30 degrees as it goes down. Pretty cool. But what happens when the air gets saturated? So if the air gets saturated, all right, that means that it's going to rise and it's going to cool eventually to its dew point temperature. Once it hits its dew point temperature, then it's saturated. That's when water vapor condenses, that's when clouds form, and that's when we also have that latent heat release. I think I remember when we talked about latent heat, I said anytime you hear latent heat or anytime you hear condensation or evaporation, think about hidden energy. Think about the fact that there's going to be a temperature change going on, even if there's no heat or cooling additional to this parcel. So that's super cool, right? We have condensation happening, which means that heat is actually going to be released into the environment due to latent heat release. Well, what does that mean? That means that now it's not going to change temperature at the same rate as it did when it was dry or unsaturated. It's actually going to warm at lesser of a rate. So latent heat release offsets the cooling due to expansion. So the parcel cools at the moist adiabatic lapse rate, which is going to be around 6 degrees Celsius per 1,000 meters. Pretty sweet. Now we have one other lapse rate. This is going to be the environmental lapse rate. This one is one that we don't just know. It doesn't have like this isn't a constant. This is going to be a variable. It changes. It's not always the same. This is something that we measure. So the air parcels don't warm or cool the same way the environment does. The air outside an air parcel has a different lapse rate, which is what we consider that environmental lapse rate. Now, we actually measure it by the weather balloons with the radiosondes. It's part of the reason why we have them going up in the atmosphere, and it's part of the reason why they take measurements at certain levels. This is highly variable. The average value is going to be about 6.5 degrees Celsius per 1,000 meters. That's something that we measure. It's going to change all the time, and it's not going to be the same. I actually just watched Aeronauts, if you guys have Amazon Prime. It's a story of one of the first meteorologists, and this guy actually took a hot air balloon and went up higher than anyone else did with this hot air balloon and took measurements the whole time. And while I watched this movie, one of the things I thought about was, oh wow, I bet you he's the one who figured out the dry adiabatic lapse rate and the moist adiabatic lapse rate, because one of the things that he was measuring was actually the dew point as he was going up. Pretty cool. All right, so here's some of these group questions. I'm going to pretend like you actually paused it. All right, let's move on to stability. So suppose an air parcel is pushed upward. Now, for the sake of conversation, we're going to just, skip over like what would push an air parcel up, because we will actually go over that here, I think, in the next video. But suppose it's nudged. It's just kind of pushed up. All right. In a stable atmosphere, the air parcel is going to resist that upward displacement and it's going to sink back down to the place it started. Remember, when we first started this video, I said if you're pushing the rock up to the top of the hill and it starts rolling back down and it ends up at the same place where it started again, that's going to be like a stable environment. That's exactly what happens with this air parcel. If it gets nudged up, it's going to want to go back down to that same place it started. In an unstable atmosphere, though, all right, the air parcel is going to continue to rise after this nudge. So just like that, that guy nudged that rock and it just kept going down the hill and it didn't end up in the same place it started. If this air parcel is nudged up, then it's just going to keep going up. It's not going to go back down to the same place it started. That is going to be an idea of an unstable atmosphere. So in an unstable atmosphere, we kind of have this right here on the left-hand side. We're going to have the unsaturated dry rate, and then on the right-hand side, we're going to have the saturated adiabatic rate. And then right here in the middle, this is going to be the temperature of the environment. This is going to be the environmental lapse rate. All right, so you can see if this helicopter, if he's pulling this up, right, so he goes up to here, all right, then that air parcel is going to be 10 degrees. It's going to be cooled down to 10 degrees, but the outside temperature is going to be 22 degrees. The tendency of this air parcel is going to actually be to fall, because it's actually 10% colder, or 10 degrees colder than the outside temperature. Even if we pull it up and it cools at the moist rate, the moist adiabatic rate, right? Then it's still going to be 18 degrees, where the outside temperature being 22 degrees is going to be 4 degrees colder, and that tendency is still going to be to fall. So in either one of these scenarios, and it doesn't matter if you go up to even 3,000 feet, right? We're still going to be seeing the fact that this air parcel, whether it's moist or dry, is going to fall due to the fact that it's always going to be colder than the outside environment. See, here's 12 degrees, here's 10 degrees, and here's 18 degrees. So it's always going to be colder, so that means it's going to fall. In this scenario, you would need to know what the outside environmental lapse rate is, and you would also need to know if it was like cooling dry adiabatically or moist adiabatically, and you'd need to have a starting point. What temperature was it at what, altitude, to have an idea. But as long as you know these things, you can always do some math to figure out whether or not this air parcel is going to sink. Now, we also have a stable atmosphere. Maybe not looking at with respect to the air parcel, but just with respect to the atmosphere itself. If we're looking at environmental lapse rate where it's going to be warmer air on top of colder air, then that's kind of like the situation that we have going on between the troposphere and the stratosphere, right? The stratosphere warms with height and the troposphere cools with height. And remember, I said all the weather stays down in the troposphere because it can't penetrate through that warmer layer. Same thing happens, though, if it's in the troposphere. Anything that's happening down here in this colder layer, generally speaking, is not going to penetrate through, because at that point, then the outside air would become warmer than the parcel itself, and it would always want to sink back down again. There's another name for this type of situation that we've talked about before. Hopefully you guys can remember if I asked you, what type of environment, what would be another name for this type of setup? Well, if you said that it was an inversion, then you were correct, because inversions are where there's warmer air on top of cold air. This happens a lot when, thinking about a couple of weeks ago, this happens a lot at night. Remember, because that's when we have that outgoing long wave radiation is coming out of the surface, and that's going to cause it to be colder right here at the surface than it is going to be above it. Now that's talking really close to the surface when we say that, but it's still or an inversion. So we can, and I think I told you at that time that it doesn't matter what situation we're talking about, anytime there's warmer air on top of colder air, we can consider that an inversion. So this would be a form of inversion. Now, let's flip over and look at an unstable atmosphere. Again, we're going to have this person inside of a helicopter rising an air parcel up. When I first started teaching this class, I could not understand why there's a helicopter in these pictures. But I've come to realize there's a little string there. I think he's pulling these air parcels up. Okay, so here's we have the let's see, the saturated air parcels of the moist adiabatic lapse rate, and these are going to be the unsaturated at the dry adiabatic lapse rate. And right here, this is going to be what our balloon, our weather balloon has measured the environmental lapse rate to be. Well, in all these situations, and regardless of which side that we're on, if we're looking at it moist adiabatically or dry adiabatically, it's always going to be warmer. So if you look at this 2,000 meter level right here, we can see that if we rise it dry adiabatically, it's going to end up being 10 degrees here, which is going to be 2 degrees warmer than the environment, which is 8 degrees. If we rise it moist adiabatically, then it's going to be 18 degrees, which is 10 degrees warmer than the 8 degrees. So regardless of what we're looking at here, it's always going to be warmer in this situation than the outside temperature. What that means is that air parcel is going to want to keep rising. Right? It'll probably start towing that helicopter with it instead of the helicopter pulling it up. We can also look at a destabilized atmosphere as well. This is where we're going to have it set up with the warmer air on the bottom and the cooler air on top. Well, now this one makes sense, right? Because if it starts off at the bottom and it's warmer air, it's going to want to rise, and it's not going to end up back down at the bottom again. It's just going to end up somewhere above where it started. All right. Now, we looked at them separately, but generally speaking, we don't have air parcels that just rise dry adiabatically or that rise moist adiabatically. Usually what's going to happen is an air parcel is going to rise dry adiabatically, so it's not going to be saturated. It's just going to rise until it cools to the dew point. So between the ground and the part where it cools to the dew point is going to rise dry adiabatically. And then once it cools to the dew point, then it hits saturation, then we're going to have clouds, then we're going to have a relative humidity of 100%, and condensation is going to happen. Once condensation happens, then latent heat release is going to happen. That's going to cause it to warm at a lesser rate. Then it's going to rise at the moist adiabatic lapse rate. So that's going to be 6 degrees per 1,000 meter. This is going to be kind of an idea of how we can look at that. We can have our nice little friend, the helicopter, pulling this little air parcel up, and the air parcel is going to rise dry adiabatically. See right here at 10 degrees per 1,000 meter. All right, it's going to go up. It's going to hit 20 degrees. Well, the dew point must be 20 degrees because then at this point is when it's going to actually hit saturation. That's when you're going to start see the bottom of the cloud. Right here. That's where you're going to see it condensation happening. And then it's going to continue to rise, but it's going to rise moist adiabatically instead of dry adiabatically. And I don't know what happened to the helicopter up here. Maybe he's disappeared in the cloud, although we can see him here, so I don't know. It doesn't need the helicopter anymore. It's just rising, I guess. I don't know. This is going to be, an unstable air, and this is going to be a stable situation down here. Due to the environmental lapse rate, which is going to bring us to conditional instability. Conditional instability is when the environmental lapse rate is between the moist adiabatic lapse rate and the dry adiabatic lapse rate. So what that means is that air that cools dry adiabatically, so it's going to rise dry adiabatically, all right, it's going to be cooler than the atmosphere and it's just going to sink back down again. Doesn't matter. It's just going to be cooler in the atmosphere, so it's going to want to keep going back down again. But if it cools moist adiabatically, it's going to stay warmer than the atmosphere and continue to rise. All right, so let's kind of go right here, right? At this point, it's going to be warmer than the atmosphere, or than the outside air temperature. So at this point, it's going to keep wanting to rise. But right here, the outside temperature is going to be warmer than the air parcel. So it's going to want to sink. So that's where we're seeing the fact that right here is going to be stable air. It's going to keep wanting to go back down to where it started from until it hits about this point. And once it hits this point, then it's actually going to be warmer than the outside air. And then it doesn't want to rise on its own. So at this point is when we have unstable air. So this situation is going to be a situation of conditional instability. Now here is the group questions. I hope you guys try to complete these on your own. I will see you in the next video.